So welcome back, everyone. And it's my pleasure to announce the second session of this morning, which is on quantum cryptanalysis. And our first speaker in this session will be Akinori Hosoyamada.
Yes.
And Akinori, could you start sharing your screen, please? And then please start.
Can you hear me?
We can hear you very well. Perfect. Yeah.
Okay. And
we can also see your screen now. Yeah.
Okay. So does it look fine? Is it
so
okay?
It's not maximized yet, but yeah, now it's maximized. We can see everything.
Okay.
Perfect. Thank you.
Then, let me start, please. Okay, so thank you for introduction. I'm Akinori Hosoyamada from NTT Secure Platform Laboratories. This is a talk on quantum cryptanalysis on contracting phase structures and some observations on some observations on related key settings on usual phase structures and contracting phase structures. This is joint work with Carol Schitt, Yunwen Liu, and Xianmei Shim. So first, I'd like to explain about our attack models. This picture illustrates the classical model of chosen plain text attack. There is an adversary who has a computer, and there is an encryption oracle. And in the quantum setting, the computer is replaced with a quantum computer. And so this model is called the Q1 model. And actually, in the quantum setting, we can also consider another attack model called the Q2 model. In this model, the encryption oracle is also replaced with a quantum one. And actually, in this attack model, the ability of the adversary is very strong because all the things, including queries, are done in quantum superpositions. And in our paper and in this talk, we use this model. Next, I'd like to explain about phase structure. So what is phase structure? This picture illustrates the 3-round version. This converts 3 L-bit PRFs, F1, F2, F3 into a 2 L-bit permutation. And here, a natural question is this permutation becomes a secure PRP if F1, F2, F3 are secure PRFs? And actually, in the classical setting, the answer is yes, because there is a security proof that this permutation becomes a secure PRP against polynomial time chosen plain text attacks. However, in the quantum setting, the answer is no, because in the attack model of Q2 model, Kuwakado and Mori showed that there is a quantum chosen plain text attack distinguisher against this scheme. So this is the summary on 3-round phase structure. Actually, we can also construct 4-round phase, 5-round phase, and so on. And next, in the previous slide, I explained about the usual phase structure, but actually there also exist many generalized versions of phase structures. And on some generalized phase structures that are secure in the classical setting, there also exist polynomial time quantum attacks, as well as the 3-round balanced phase structure. For example, the D branch 3 minus 1 minus 3-round type 1 generalized phase structure is secure in the classical setting, but can be broken in polynomial time in the quantum setting. However, there has been few works about quantum attacks on a generalized version called contracting phase structures. So what is contracting phase structures? We call that the phase structure looks like this. This picture illustrates the single round transformation of phase. And now the contracting phase structure looks like this. Now it has many branches, and its characteristic is that before the round function, the sum is taken over all branches except for the rightmost one. This is the contracting phase structure. And as I mentioned before, there exist few works on quantum attacks on contracting phase structures. In the classical setting, there is a work that claims that D branch 2D minus 1 round contracting phase becomes secure in the classical setting. This is the result in the classical setting. So after seeing this result, we had this natural question: can we break this scheme, this contracting phase structure in polynomial time? This is the starting point of our research. And we showed these results. First, there exists a polynomial time QCPA distinguisher on D branch 2D minus 1 round contracting phase. And second, when each round function has this form, that is, there is a public function fy, and the round TKI is directly added to the input. and I call this structure as facial KF structure. Then we can also recover the keys. That is, we can mount not only a distinguisher, but also key recovery attacks when the round function has this form. And finally, we also showed some quantum-related key attacks. Actually, I don't have enough time today to explain about the details of, about related key attacks. So please check our paper for details. And all these attacks are based on Simon's quantum algorithm. And more rounds can be attacked by combining Grover's algorithm. And actually, very recently, we noticed that Hozik and Knudsen published a concurrent work, a quantum distinguisher for 7 and 8 rounds, SMS4 block cipher. And here, SMS4 is a Chinese national standard block cipher, which uses the contracting facial KF structure. They also showed polynomial time distinguisher on 7-round contracting facial KF. And on the other hand, we show polynomial time key recovery attacks on facial KF and some related key attacks, but they do not show such an attack. So this is concurrent and independent work. And this is again our main result. We showed some distinguishers on contracting facial KF, and we also showed some key recovery attacks on contracting facial KF structure, and we also showed some related key attacks on balanced facial KF and contracting facial KF structure. This concludes today's my talk. Thank you for your attention.
Yeah, thank you very much for this nice presentation. Are there any questions?
The related key attacks you used, is it like some particular relation that you exploited, like linear or like, I don't know, like quadratic or something? Or
could you please say it again? I'm sorry, I couldn't hear.
Oh, sorry. I mean, the related key attacks you use, the related key family usually belongs to a particular functions like linear or quadratic or something like this, or affine.
Yeah.
So do you have like any particular class of related key that you exploited in this?
Yeah. So actually, we assumed that the adversary can inject arbitrary difference on particular round key.
I see. So the arbitrary difference, that's independent of the key, I guess. Like that's like a fixed thing, like delta.
Yeah, something like that. Yes.
Got it. Okay, thanks.
Thank you for question. Thank you.
Are there any other questions? So I was wondering, this may be a very, very naive question that I'm having. Yes. Is there some way that you can say that if you just use enough rounds for, well, sufficiently large values of enough, at some point also in this quantum attacker setting, things will be good again? Or is this basically, can you like when you look at key length and Grover's algorithm, we basically know, okay, we in a very abstract attack cost model, we double the key length and then quantumly everything is fine. Is there anything that you can say about if we have this kind of general physical structure, if you just make enough rounds, at some point it will also be fine in the quantum setting?
Okay, actually for the balanced usual facial structure, there already exists some proof. For example, I explained that this structure is insecure in the quantum setting, but if we add one more round, then the scheme becomes again secure. And for contracting facial structures, I don't know any proof, but I expect that it will be secure when we iterate many more rounds, I think.
Okay, thank you very much. And then, yeah, please, everybody, keep asking questions in the Zulip chat, and then the authors, I think, will also keep an eye out there and then be able to answer there, or we have maybe time to run some more questions at the end of the session. Then I think we proceed with the next talk. So, Akinori, maybe you stop sharing your screen, and then Ravi can start. So the next talk will be given by Ravi Anand.
Hello, am I audible?
You're very well audible.
Okay, I'll just share my screen.
And that looks perfect. So yeah, please,
yes.
please start. Perfect.
Okay.
Yes.
Thank you. So our work is on evaluation of quantum cryptanalysis on SPEC. So there is a joint work with myself, Arpita Maitra, and Saurabh Mukhopadhyay. So in this work, we actually implemented Grovers on SPEC by creating a reversible quantum circuit on SPEC, and then we estimated the resources required to implement Grovers. And then we also implemented quantum differential cryptanalysis on SPEC. We created a toy cipher of a SPEC-like cipher and then implemented it on Qiskit and IBM-Q to see whether it works or not. So we know that SPEC, the state of the cipher is updated something like this, and state round is this, and the key sequence are created like this. So first we create the circuit for the key expansion, which can be done like this. And in this, so if we suppose m is equal to 2, then we need 2 keywords for this. So first k0 is directly used in the first round, and then k1 is created for the second round. So we create the function something like this, where RR alpha is you rotate it alpha times, then you add this to here, and then you add this round constant, which depends on the round number. And then at last, whatever the value comes here, as you can see here, it is rotated beta times left and then XORed with us. In this way, we can create the round functions and then use it accordingly. As for the round update function, the circuit can be created something like this. So K0 and L0 is the round keys. Sorry, K is the key. L0 and R0 are the left and the right of the state. So first, as it is here, we can create this L0 is first rotated left times, and then R0 is added to it. Then the key is XORed here, and then this whole function is XORed here in R0. So L1 and R1, these are the second step of the state update function, where key is the key expansion, which I've already discussed above. So the complete circuit for this SPEC can be created something like this. So we do it for the T rounds expansion, and then where U is this round update, which I said before, and K is the key expansion, and we get this LT-1 and RT-1, which is the ciphertext. So we use this in our toy SPEC, which is of state size 6 and alpha and beta are assumed to be 1. And we find that then this is the circuit which was obtained in IBM Qs. And this was the result 101, which is actually the result that we needed here. If you can see, L2, R2 is 101 and 101. So we implement this. Now we implement these Grovers on our that toy cipher which we had discussed before. For the plain text is this m is equal to 011 and ciphertext, and the outcome of the application should be 110010 as I had said here. And this is what we had obtained here with a very high probability. So here, sorry. So here actually this gives a better probability in SPEC when compared to Simon, which we had there was a previous paper. And then we estimate the resources required by using all these three. So one round of key expansion requires these many C0 gates and Toffoli gates and I0 gates, where here I is the round number. So in the first round number, in 0, there is no round constant. In 1, there is just the round constant is 1 similarly. And one round update requires this much and these many Toffoli gates. So T round of SPEC would require T round updates and T-1 key expansions. So this way we estimated the resources to be this. And then to run for cost of the exhaustive key search, complete key search, we ran the Grover's algorithm for 2 to the power k by 2, and then we can estimate that the results are almost something like this. These are all approximate numbers almost. And in the second part, we implement quantum differential attacks. So first thing we did is to find if we can find differential distinguisher using Grover's algorithm. So in a general way, if we have to, in the distinguisher, we try to find a pair of plain texts which satisfy this. So if the cipher is random, obtaining such a pair would require 2 to the power n trials. But if it satisfies, sorry for that, if it satisfies a certain this, then it would require only 2 to the power p plain text. But sorry, for the quantum adversary, this will only require, I mean, if there are p plain text, the probability of obtaining a trail is p, and we would only require 2 to the power p by 2 Grover's iterations. So we implement this on we obtained this 4-round differential trail on the toy cipher that we had constructed before, where p is equal to 2, and we obtained that, we got this value 001 111. The number of qubits in the IBM Q that we can use is only 32. So we obtained here just one plain text, but we can modify the code so that we get both the plain text pairs. So here we computed it. The first P we obtained here was this. We computed the second pair there, and the corresponding ciphertext after 4 rounds are this and this. And then B dash is this what we had obtained, what we wanted. In the second part, we run the key recovery attack on it. And so if we have this trail here, where R is the number of rounds with probability P, then we can extract the secret key using these three phases: the collecting, filtering, subkey, and the brute force. So in collecting, we try to apply Grover's over all possible pair of plain text such that we get a pair M which satisfies that trail. In the subkey guessing phase, we go back one, decrypt it one round, and then try to find out those only those subkey which gives this XR and YR. And in the last, we try to brute force all the remaining M-1 round keys. So the complexity of this differential attack comes to be this one, where C is pi by 4. And because we have 2 to the power pi by 2 iterations for running the differential trail, and then one round decryption, so these many. And since we are searching for M round keys, so this is this. So this is the total complexity of this attack. So we ran this on a toy cipher where we have these following assumptions: that we have a trail of 5 rounds, and then we recover. We run this attack for 6 rounds and try to recover the last round key. So we can see that. So in phase 1, we tried to find the plain text pairs which would satisfy that given trail, and we found here. This is the result. And in phase 2, we tried to find the round key which would satisfy that sixth round subkey, and as expected, the output was this. And in phase 3, since we need to find one more round key, we found the round key here. So our key that we needed was successfully found here. So we estimated the resources using this, and then we found that we needed these many qubits, classical bits, these many measurements were required, and total gates required was these many, which is made here. So for total, these assumptions were based on this differential computed by F. Abed et al. In their paper, Differential Cryptanalysis, which was presented in FSC 2014. So in conclusion, in this work, we perform quantum cryptanalysis on SPEC, and then we analyze what are the resources required to compute that, and then we implement the quantum cryptanalysis on, differential cryptanalysis on quantum framework. Thank you.
Yeah, thank you very much for this very nice presentation. Are there any questions?
Chat seems not that active.
Yeah, people are still waking up, certainly in Europe.
Yeah, waking up, I guess.
Yeah.
Or about to go to sleep in the Americas. So.
Yeah, I guess East Coast has already slept, so West Coast still.
All right. And if there's no questions, then I would say thank you to you for this very nice talk, and of course also again thank you to Akinori for the first talk of this session. And please, if there's any more questions popping up when people are sufficiently caffeinated in Europe or otherwise, then please write them to the Zulip chat and engage in an active discussion there. And then this concludes the second session of today. And there might be some announcements now, so I will hand over to the organizers now for those announcements. Thank you again.
Thank you, Peter and Pratyay. So we will see you again as session chairs on Wednesday, same time.
Sure.
And also
thanks.
your talk, Pratyay, tomorrow, right?
Oh, that's tomorrow. Yeah.
Okay. Yes. Yeah. Thanks a lot again. So in about half an hour, we will be streaming pre-recorded talks. They are non-interactive. So authors will not be there, but we have a Zulip chat session for that. So you can post your question and hopefully authors will respond to that later. So our next live session will be at 6:30 p.m. India time, and that is 1 p.m. UTC. So thank you, and see you.
I guess everybody's, it's a lunch break, right? Everybody's on their own for their lunch.
Yes. Yes.
All right, see you in the afternoon session.
Yeah, see. Thanks, bye. I'll stop the streaming and close.